Hi everybody. In this video we are going to look at diffusion, modeling a diffusion equation using this equation from Crank. It's Crank 1975. The title of the work is Mathematics of Diffusion, and if you type that into Google you can get a free PDF that you can download if you want to see these equations and many others. So this is the solution to a differential equation that tells us the concentration of some component X. In this case, we'll look at nitrogen in groundwater, but it doesn't really matter what we're looking at. And that concentration at some distance x will depend on the initial concentration, C naught here, multiplied by 1 minus the error function of x, how far away we are from this point source that has a value of C naught, and then divided by the square root of 4 times d, the diffusion coefficient. That tells us how fast the material is moving through the medium. In this case, it'll be nitrogen moving through water. And then t, how much time has elapsed. So the concentration at any position x here, some distance from C naught, the point source, will depend on how fast the stuff moves, d, and how long it's had a chance to move, which is t. So we're going to use these variables here. Our C naught will be 200 milligrams per liter. This will be our diffusion coefficient, 0.0188 in square centimeters per second. And then elapsed time, I'm going to enter it in hours, but since these units are in second, we'll use this value here. And then there's an initial concentration in the sink. We'll get back to that in a moment. Let's try building the model. We'll graph it, and that'll help make sense of the whole thing. So I'm going to set up meters or distance in meters, and I have it varying from -1 to +1 in units of 0.05. And I use 0.05, so as you'll see in a moment, we'll get a nice smooth curve. The units for the d value are in centimeters per second, so we can convert that to square meters per second. But instead, I think I'll just do the calculation in meters, but then chart, well, we'll do the calculation in centimeters, but chart it in meters. So we'll just take equals 100 times whatever the total meters are, and then we can fill down towards to the bottom of our entries here. And then we're going to calculate C sub x. And C sub x will be equal to, well, whatever we get from this equation. So it'll be 0.5 times C naught. When we fill down, we don't want that row 2 to vary, so we'll put a $sign in front of that. And then we're going to multiply that times the quantity 1 minus the error function. So in Excel, it's just ERF. And then it's the error function of x, which we'll take in centimeters, divided by the square root of 4 times the diffusion coefficient. We want a $sign in front of the 3 times time, which we'll take in seconds because we've got square meters per second, and we don't want that to change. That's going to remain constant. So put a $sign in front of the 4. Then we'll close the parentheses on the square root, close it on the error function, and then close it on those initial brackets. And that should work, and it seems to do so. So we'll fill down and edit fill down. There we go. And we have values ranging from approximately 200. If we make this a small enough value, we go to, let's say, -10 meters. That should get us to 200, but we'll just put in a value of 1. So we're going to look at how the concentration of nitrogen in groundwater, for this example, varies as a function of distance. And so we'll take these values and insert an XY chart, and there's our curve. So here's the diffusion equation, the results of the diffusion equation. We have, we'll put in some XY titles so we're very clear about what we're plotting. So here we've plotted the distance x. This is the distance from the point source of contamination. And over here on the y-axis is the concentration of, in this case, what did we plot? We plot nitrogen and groundwater. I'm writing nitrogen and groundwater. I don't know if this is a realistic concentration, but that's the diffusion coefficient that I picked up from a website. So as we get closer and closer to the source at minus 100, at negative values, we approach the initial condition, which is, or the boundary condition, which is 200 milligrams per liter. As we get close to zero, that's the interface, we get something that's halfway between the point source and the background, which is down here, which we let equal to zero when we used this equation. If we wanted a case where the background or the medium that's being contaminated does not have zero nitrogen, we'd use this equation instead. So instead of C naught, we have C naught minus CF. So it would be 200 minus, let's say, this value here, which is 190. And then at the end, you'd have plus whatever that final concentration is here. I write F for final. That's actually probably not a very good notation. Could be CM for medium. Since we've plotted a model, we can double click on this just as a stylistic issue. I like to take away the markers because if we have symbols, it can look as if we were plotting data and not a model. Here we're just plotting a model, and so we'll take away the symbols and just plot the line. And did that not work? We'll try it again. We want no marker, and then for the line, we want a solid line. And there we go. This time it did. And then for the axis, it's a little bit cleaner if we have the vertical axis crossing the x-axis at, well, we could make it minus, oh, this is fine the way it is. We don't want to change that. We could have the x value crossing at minus 1.5, and that'll get that x-axis, the vertical axis, out of the way. We don't necessarily need to mark where the interface is. Now, this is for a case where we have 10,000 hours that have passed by. If we have zero time that has gone by, then we get a, well, that's not very helpful. Let's try this. Let's say we have a tenth of an hour. Then we get something like a square function. This line here, it has a bit of a slope. But if we took a smaller interval here, this would really be essentially a vertical line and would get a square function because we'd have the initial concentration here from the contaminated point source and then a background that still has seen no contamination yet because not enough time has passed by. If we could make this smaller, we're not going to see any change in the slope because we don't have a fine enough of a scale. But if we, instead of a 0.05 scale, we went, let's say 0.01 meters, then we'd probably see this steepen a little bit. As time goes by, let's say we have 20 hours, or that's not visible, 100 hours, we get to see a little bit of a curve, change it to 1,000, change it to 5,000. The longer time that the longer the amount of time that passes, then the steeper or less steep the curve gets. If we have the curve, if we let a very long period of time go, then we get a much shallower slope. So I've just put in, go back to 10,000 hours again. So under 10,000 hours, that's how much diffusion has taken place. Let's say we wanted to compare the curve at one time to another time. So let's say we wanted to compare 10,000 hours to, let's say, 30,000 hours. Well, what we could do is just copy all of this, paste it over here, and we'll click on our equation, make sure that all the cell references have been transferred over, and they have. We're referring to these cells over here instead of these over here. And so what we can do is let this set of calculations here be conducted relative to 10,000 hours, but we can make this, well, let's say 50,000. Let's see if that makes an interesting difference. And then what we'll do is we'll plot these data calculated at 50,000 hours and plot them on top of the same curve. So we want to go to edit. Let's try this again. we lost the copy portion. So we'll go to edit copy, and then edit paste special, new series, and the X values. And there we could compare the case for 10,000 hours versus 50,000 hours, or any other time you like. We could compare it to, let's say, 2,000 hours instead. And we can plot a series of these curves to say, well, if you're at this position here, let's say you are, let's zoom in a little bit. If, let's say, you are a half a meter away from the point source, or excuse me, from the interface, so if you're a half meter away, then after, let's say, what do we put in, 2,000 hours? After 2,000 hours, you're not going to see very much contamination at all, but after 10,000 hours, you're going to get some detectable contamination. It looks like about maybe 15 milligrams per liter in the units that we're using. So that's how we plot diffusion equations using these equations from Crank and entering them into Excel. We're letting the time vary. The C0 is fixed and the diffusion coefficient is fixed. And we're just comparing how distance and time affect, let's say, contamination of some given point source. Could be nitrogen in groundwater or arsenic in groundwater or forced right content in an olivine. That all work pretty much the same way.